So thank you for the invitation. It's a pleasure to be here. I'm going to talk about joint work with Charles Fefferman, Sergey Ivanov, Yaroslav Kurilev, and Marty Lasas on fitting a manifold to noisy data. So in machine learning, there is a subfield which is known as manifold learning, where the hypothesis is that high-dimensional data often lies near a low-dimensional manifold, and that this fact should be exploited to reduce the sample and computational complexities of various tasks of interest. So when this is actually true, we say that the manifold hypothesis is true. So I'll give you one instance where this is a very reasonable hypothesis, the example of Cryo EM. And I'll talk about testing the manifold hypothesis and finally finding a good guess or a good fit manifold if the noise level is not too high. So in Cryo EM, what happens is you have a thin layer of ice in which you have lots of large molecules embedded in random orientations. You shoot an electron beam at this collection of several thousand molecules and take shadows. Take the the shadow of all of these from screen that's behind. So what happens is you essentially are evaluating the integral of some sort of some electrical potential as the electron beam passes through these molecules in their random orientation. So you get these shadows of randomly oriented proteins, and from all of these shadows, we want to reconstruct the three-dimensional structure of the protein. This is essentially what happens. However, there are several challenges because this is a very noisy process. So the signal to noise ratio is very small in the whole thing. So you essentially have very noisy pictures, and we need to find the three-dimensional structure of the molecule. So why is this a question in manifold learning? It can be viewed so because the orientations of these molecules correspond to the action of a Lie group, SO3, the group of rotations in three-dimensional space of a molecule. So you think of this molecule as a function from a ball in 3 dimensions to the reals, giving electron density or something of the protein molecule. And you imagine this group rotating this whole molecule, you get different functions. So this is like an infinite dimensional representation of SO3 because you have SO3 acting not on some finite dimensional vector space, but an infinite dimensional vector of functions, which we can take to be L2. But in practice, you're going to take these pictures at some resolution, let's say 200 by 200 pixel pictures, and you're going to get a 40,000 dimensional picture of the shadow. So it's a bit like, it's a lot like having SO3 act on a 40,000 dimensional vector space, but it's a smooth action because as the molecules turn smoothly, the images also evolve smoothly. And this causes the trajectory of all possible images of a fixed molecule to lie on a manifold that is like SO3, diffeomorphic to SO3, in the generic case. So if the molecule has symmetries and so on, then it's not going to be SO3, it's going to be a quotient of SO3. But if trees, then in the generic case, the trajectory of possible rotations of this molecule is going to be a three-dimensional object intrinsically, rather than a 40,000 dimensional object, although it's embedded in 40,000 dimensional space. So here are some images. These are 200 by 200 images of a molecule. This is it can be viewed as noise. As you see, there is a fair amount of noise. So the noise actually has been removed, but even so, you see that it's a noisy picture. And so the model that we'll have in mind is that you have this low-dimensional submanifold of a high-dimensional space. So I'm going to give you some idea of what a manifold is in greater detail later, but for now, just imagine it's a low-dimensional surface embedded in high-dimensional space. but with a lot of Gaussian noise. So you have this generative model, which is pick a random point on this manifold, add a large Gaussian vector, or in our case, it'll actually be a small Gaussian vector, and reveal the point, and so on. Keep doing this. And from this data, we will be interested in testing whether there is a nice manifold underlying the data, or in some cases, we'll be interested in finding the manifold. So the first question is, in some more general setup where you just have data, can we test if there's a low-dimensional manifold underlying this data? How many samples do we need to perform such a test? And answers to these questions are provided in work with Fefferman-Mitter-N, which appeared in the Journal of the American Math Society in 2016. So I'll have to make some restrictions, place some restrictions on the complexity of these manifolds. Otherwise, we won't be able to talk about what's the number of samples required to find or declare the non-existence of such a manifold. So the assumptions are, firstly, these manifolds don't have a boundary. They are not, for example, like a disk in R2, because the disk in R2 has a circle as a boundary. These are more like the surface of a sphere in R3. So there's no boundary. They are twice differentiable. The reach, which I'll define soon, is at least tau. And the d-dimensional Hausdorff measure, essentially the d-dimensional volume, is at most V. So M has no boundary, d-dimensional. C2 means that for every point in M, there is a epsilon greater than 0 and a ball such that the intersection of this ball with the manifold is a graph of function from a d-dimensional disk to the normal space. So, for example, if this is my manifold, I take a point here, I take a ball around this, I take the tangent space over here. Since it's twice differentiable, I can take a tangent space. And this is the graph of, this is going to be the graph of a twice differentiable function from a subset of the tangent space to the normal space. So it's a lateral perturbation of this disk locally. So that's what we mean by a manifold. What we mean by reach is the following. It is the largest number with the following property. If I have a point at this distance from the manifold, then there exists a unique nearest point on the manifold to the point I have. So there are many equivalent definitions, but I'll just mention another, which is that it is the largest tube you can have around the manifold, before which the boundary of the tube will start developing, will cease to be a manifold in the sense we have described. So what happens if you exceed the reach is that you will start having self-intersections for the boundary of a tube around this manifold. So here example is something with large reach, because I have to go pretty far before which I have a point which has two nearest points on the manifold. Here on the other hand, the reach is small, because even here there are there's a point, just two nearest points on the manifold. So this is some notion of inverse curvature. The larger the reach, the smaller the curvature. But additionally, it also encodes some global geometry. So for example, if you have two infinite lines at a distance of 2 tau from each other, the reach of this union of two lines is tau. Because when you take the tubes of distance tau, those two tubes will intersect exactly at one line. And that's not allowed, for, that's not a good situation. So that's where the reach, that's the reach. So the d-dimensional Hausdorff measure in our situation is the same as what's known as the Minkowski content. It is something that you can evaluate by just taking tubes around the manifold which are very thin, and then dividing by a normalizing factor of volume that is the volume of d epsilon of dimension that is n minus d. N is the ambient space dimension, and d is the dimension of the manifold. So here's the question that we answered in 2016. Suppose P is an unknown probability distribution supported in a unit ball in a separable Hilbert space. So it can be infinite dimensional, but it has to be separable. And x1, x2 are IID samples from P. Given epsilon d V, tau, and confidence 1 minus delta, is there an algorithm that takes a number of samples depending only on these parameters and not on the dimension of the ambient space, which could even be infinite, and outputs whether or not there is a manifold in the class GE, which is the class of all manifolds which have dimension D reach at least tau and volume at most V, such that with high probability the expected square distance of a random point from P to M is less than epsilon. So note that here I will require an oracle that tells me the inner product between two vectors in the ambient space, because otherwise that itself will cause some dependence on the computational complexity of the process, which will depend on the ambient dimension.
Sorry, does this algorithm also give some kind of specification of the manifold? Or?
Yes, it does.
I see. Like again, some kind of, you have an oracle, I'll give you a point, it'll tell me whether it's close to the manifold or...
So that can be done. What we have done will become clear in a little while, but it's an implicit, so it involves an implicit characterization as a solution of some equations. So that is what the manifold is. But such an oracle can also be computed because of the nature of the equations involved. So yeah. So first there are two aspects to it. One is statistical, one is algorithmic. The first statistical question is how many samples do you need to test this hypothesis that there exists a manifold in GE which is epsilon close to the measure in that least square sense, in the square distance sense. So the main result here is that it does not depend on the ambient dimension, which, as I said, can even be infinite. Yeah.
Do you specify your D ahead for your task?
Yeah.
Isn't that a crucial part of what you need to figure out?
So yeah, I mean, we are viewing this as a black box that we can supply. So then now users can form a grid or whatever they want, and then ask questions of use this to do adaptive queries. Yeah. So the theorem here about the sample complexity is that the sample complexity looks like this. It is exponential in the D, the intrinsic dimension, polynomial in all the other variables. And if you have this, then the so-called empirical risk minimization procedure will succeed. So what is the empirical risk minimization procedure? It is, I pick a certain number of random samples from P, I find the best fit manifold to these things magically, and claim that this thing will perform well according to the true loss function, which is something I'm not given, which is something that involves the integral over the probability measure of the squared distance from a random point from that measure to the manifold. So this is a standard kind of thing that in statistical learning theory, where you bound the complexity of some function class and then do things. The thing that is surprising here is that there is no dependence on the ambient dimension, although all these functions live in some very high dimensional space. So somehow the fact that these manifolds are low dimensional is good enough to get rid of the dependence on the fact that the probability measure itself lives in a very high dimensional space.
Isn't the covering number of the probability measure all that matters in the entropy basically? So basically these results are saying that the entropy is independent of the ambient dimension.
That's right. So it's the entropy of the function class. So this is independent of the probability measure as long as the probability measure is supported in the unit ball.
Sorry, yeah. So, but that is, in that sense, I mean, the fact that it's totally independent of the ambient dimension is indeed surprising, but this is in the same line as the other results, which, okay.
Yeah, so that's the statistical question. And now this is the algorithmic question. Suppose I have these points. How do I optimize my manifold so that they are, I get nearly the best fit to these discrete set of points? And so we have a theorem here. It's not a good, nice complexity, but we have an algorithm that works. So it's doubly exponential in D, the intrinsic dimension, but like I said, D can be 3 in the Cryo EM question. D is 3, so doubly exponential need not be that bad in some cases. So if you have this, doubly exponential complexity, then you can tell whether there exists a manifold which is squared distance epsilon away from the data, or the opposite case is that there is no manifold that is squared distance epsilon from the data. And note that there's a large constant here, so I'm not exactly separating at epsilon. It's either less or equal to epsilon, or I can say that there's nothing less or equal to NC epsilon. So there's a gap. You need this gap, otherwise it becomes difficult. And also, even in the class of manifolds, there is I'll either say there's a manifold in this class dv tau, or I'll be able to say no, there is no manifold in the class cv tau by c. So this is like, it's basically because if the two classes that you're trying to separate are just arbitrarily close together, then you're going to have some difficult cases. So they have to be sufficiently far apart. But these C's are universal constants. So how is this done? I'll try to get into that. But first, I want to talk about what is the content of this talk mostly, and that is that now you suppose there is a manifold. And you have samples from this manifold from some nice measure, which has got a good derivative with respect to the uniform measure. And you have Gaussian noise. So you have Gaussian noise. And the Gaussian noise is such that the amplitude of the noise is small compared to the reach. Okay, so this is a rather strong condition. This can be weakened, but I won't talk about doing that in this talk. So if that is the case, then we want to be able to find a manifold that is pretty close to the real manifold. So this question has been handled in the literature by Genovese et al. Larry Wasserman was also a co-author in this. So this was building over work by Ozertem and Erdogmus. So the result says that if you have n samples, then you can find the output manifold to within a Hausdorff distance of log n by n raised to 2 by capital T. This is the ambient dimension, plus sigma squared log sigma inverse, where sigma is the standard deviation of the noise. So what is Hausdorff distance? If you have two manifolds, the Hausdorff distance is the farthest point. So it's going to, in this case, measure the distance from here to here. Okay, so it's basically you look at this manifold and you look at all the points, you measure the distances of the points here to this manifold, take the farthest one, in which case this is this. Similarly, you do the same on this manifold. You look at every point, look at the distance, take the farthest one, in that case it is this. But maybe this distance is more than this distance, in which case I'm going to choose this distance to be the Hausdorff distance. So it's somehow how much the true manifold juts out from the manifold you present. So this is a natural way of describing sets or subsets of Euclidean space, the distance between subsets of Euclidean space. So in this talk, we improve these bounds in several ways. Firstly, this sigma square log in sigma inverse is made order sigma square. That's not so important. But what is important is that if you want to make D large, like in our case, we had D equal to 40,000, then if you want this to be roughly sigma or sigma squared, n has to be 1 upon sigma raised to something like 40,000. And that is very, very large. So the number of samples you need before which this algorithm will produce a good manifold is very large. So we can do with a number of samples that depends only on the intrinsic dimension, which was 3 in our setup for Cryo EM. And so it's this many samples, and we also get comparable error, order sigma squared. And further, we guarantee that the output manifold will have a reasonable reach. It will not degrade by more than a polynomial factor in the intrinsic dimension. So the basic algorithm is going to be you fit disks to this manifold, and you somehow morph these disks so that they merge together to form the output manifold. So in order to find the disks, this is basically a question of learning the tangent spaces in a noisy setting. So the algorithm basically does the following: you have you have this sort of noisy data, and you want to learn the tangent space at one of the sample points. Let's say here, you're really interested in this point's tangent space, but you have only samples. So let's say you pick one of these, and you want to get a good approximation to the tangent disk at this point of radius r. So what we do is we build a orthonormal basis of tangent, nearly orthonormal basis of vectors of length r centered at this point using this noisy data. If the noisy data is sufficiently close to the manifold, the span of these vectors will be a good approximation of the tangent space. So that is the idea. And so that requires a proof, because the idea is that you do require some approximate orthonormality, because otherwise you can have some very unstable kind of situations where you have a bunch of vectors that point almost in the same direction and their span wildly oscillates. We don't want that. That's why you have this approximate orthonormality constraint.
Sorry, and the disks are d-dimensional disks?
D-dimensional disks.
But at a point, won't you have like many potential d-dimensional disks? Like, how do you? I mean, I'm just trying to visualize it.
So R is going to be large compared to sigma, where sigma is the noise. In fact, square root d sigma is noise. But either way, so the issue is this. So let's suppose that this is the manifold, the board, and you have these samples which are actually either slightly above or slightly below this. We are embedded in R3. Actually, we are embedded in much higher dimensional space, but that's not so important. Now what we do is we pick these points which are somewhat far away, but they're approximately orthonormal. Now their span is going to be a good approximation for the tangent space. Yeah, so that's... So that's what this algorithm does. You get these disks, which are good local approximations to the manifold. And this is just a statement that the Hausdorff distance of the disk that you find to the tangent disk that you actually care about is going to be small. This is a lemma. So now what we do is you find all these disks. So you have this manifold, and you find lots of these disks, which are pretty good approximations to the tangent disk. The question is, how can we patch them all together to get a good output manifold? And so there are some conditions which I won't go into, but so even before that, I'll say something. So note that we said that we're going to get to within sigma squared of the manifold and not just sigma of the manifold. So that requires some averaging, because otherwise the distance that the samples have from the manifold is actually sigma. But the point is that these are IIT Gaussians, and at a very small scale, your manifold is looking really flat, but you have all these things that are distributed evenly all around. So if you average them, you get something which is order sigma squared. Now, why can't you do better than order sigma squared? Basically, sigma is the noise in the horizontal direction. So these noise vectors are spherical. So if I start from here, I'm not going to get a normal point here. I'm going to go order sigma in this direction, and then order sigma in this direction. So I get a point somewhere here. So there's no point, there's no use in taking a disk of radius less than a sig. So it turns out so for the averaging purpose, it has no point in taking a disk of radius less than sigma, because the sideways error itself is sigma, and so effectively, the error in this direction, which is called the errors in variables in statistics, is order sigma. So if I take something of this sigma, and I have a quadratic function which is corresponding to a graph of reach 1, the kind of curvature I'm going to see is order sigma squared. So this is going to be order sigma squared. just due to even the actual graph is going to vary a bit by order sigma squared. So there's no hope by just averaging of getting better than sigma squared. So what we do is we just take all the data in this tube and we take the mean. And we get one sample that is guaranteed to be within order sigma squared of the true manifold. And then we do this again for another tube, and so on. So in this way, we get an approximate net of the manifold whose Hausdorff distance from the manifold is order sigma squared rather than the samples which were order sigma. So as I said, this is the sigma that I talked about. But even before that, we need to set the stage, so to speak. And to do that, we have a first stage where you do order square root sigma, and you just get the things you're going to consider, and then because when you do this averaging, you need you don't know this disk, right? You just know you need a base to do the y direction averaging, and that base is given by this big disk of radius square root sigma. Once you do that, you take the points which are now at sigma squared from the manifold and use them to get a new set of data samples after the averaging, which are of distance sigma squared from the manifold. So now the question is, I give you a set of points which are at distance sigma squared from the manifold, which are also form a nice enough net of the manifold. Can you produce a good approximation of the manifold with good reach? And that is what I'll describe next. So I don't think I have time to go into all the math, so I'll just tell you what it is roughly. So the idea is we have these disks of radius sigma, and we have these balls. So there is corresponding to this thing, there is what we call a vector bundle consisting of all the vectors which are orthogonal to this d-dimensional disk. So it's like you have at every point I have a plane of dimension n minus d. Okay, so these are going to be basic objects. And what I'm going to do is, I had all these disks, right? So I'm going to take all these disks, and I'm going to use those vector bundles, these are called vector bundles, over the sphere, over the balls, and somehow paste them together to form a nice, smooth object. And how is that done? That is done by associating with every point the projection onto the projection onto the it could either be the d-dimensional or n minus d-dimensional subspace. So let me just check. So by projection onto the n minus d-dimensional subspace. So you take this and you get a matrix out of it, the projection matrix, onto the n minus d-dimensional subspace. The point is that now I have another ball here, and I have another disk, and I want to get a smoothly varying vector bundle, not something that changes in a discontinuous fashion. So what we have to do is we take these projection matrices pi I and merge them together using what's called a partition of unity. This is some smooth bump functions. So this is like you just sort of add them up with some coefficients, and that gives you a matrix valued function of the ambient union of balls. Okay, but these matrices are not always projections, because when you add linear combinations of projections, you don't get projections. So what you do is you take these matrices, they're really close to projections because the disks agree very well, and you take the nearest projection matrix to this matrix. So this matrix is not a projection matrix, but you take its basically large eigenvalues, large eigenvectors, take their span, and that span is taken to be the new vector, the fiber at this point. So in other words, you take the nearest projection matrix to this matrix. So that is how we get a smooth vector bundle. So this is actually a very important frame of reference, because one problem when you're dealing with manifolds is that they're not always orientable and so on. And unlike where you have graphs of functions, you cannot take convex combinations of them conveniently. You cannot take linear combinations of them conveniently. But once you have this bundle, you can actually do that. So you take this bundle and you then you define an auxiliary function using these disks, which is like the squared distance of to the manifold you don't know, but you find that function using this formula. And then you look at the set of all points where this function is stationary along the corresponding fiber. So this function is not stationary everywhere. So what does this function look like? It looks like the squared distance to this unknown manifold. So these things, they can have gradients which are parallel to the manifold. It's just that they don't have gradients perpendicular to the manifold, components perpendicular to the manifold. So what you do is you define the manifold to be a set of all points where this function f of x has a gradient that is orthogonal to the corresponding fiber. And what is this fiber? These fibers are these things I created using all this stuff. Okay, so this locally it forms a nice set of equations. The point is that these set of equations patch together nicely as you move from one point in the manifold to another. Yeah, so that's what this is. So you define the manifold with a set of all points such that this pi x, which is an x-dependent quantity, applied to f of x is equal to 0. So this f of x is a vector-valued quantity, and this is 0. Pi x is a projection matrix that depends from point to point. So this is some analysis that tells you that the reach of this resulting manifold is good. So what happens is that when you're dealing with these disks, at any point the number of disks that will be interacting will be exponential in little d, simply because that's how d-dimensional space works. So unless you do some special things which even so will not really help, but the point is that you're going to have lots of interacting disks, and if you're not careful, that number of interacting disks is going to find its way into the reach. So here there is some analysis that uses Holder's inequality, and we get some dependence that is only polynomial in D. So I won't go too much into it. I'll just say that it uses Holder's inequality. So here's a picture. So these are those fibers that are changing from point to point. So here n is 2, d is 1. So n minus d is 1. So these are one-dimensional lines. These are changing from point to point. So when they were originally defined in a ball, they were all parallel. But when you put two balls together and you do that procedure of taking the linear combination of pi I, where this is the x-dependent quantity, and then taking the nearest projection matrix and taking the corresponding kernel, you get a moving set of lines. And we need that moving set of lines. We define the manifold to be the set of all points where the gradient of the function is orthogonal to the corresponding fiber. That is how this manifold is defined. So I think so how do you analyze something like this? As I said, locally this is the system of equations. You need to talk about the reach of the system of equations, which boils down to a question about the second derivative of the solution of a system of equations. And that second derivative can be computed by calculus. So what we used was some sort of quantitative implicit function theorem, which said that if you have a nice C2 function and the Jacobian satisfies certain conditions, and the C2 function has a small Hessian, this is a C2 function which is a function from Rm plus n to Rn. So it's not a scalar valued function, but nonetheless in every direction, if its second derivative is good, then the zero set of that function will have small curvature. So we have such a result. And so you apply this result, and then you can get that the output manifold has good reach. So So what also goes into this is, so you will have to do things like twice differentiate these lines, which are actually n minus d-dimensional planes. So these matrices that you get, you'll have to compute their second derivative. And that can be a daunting task. After all, how did I define the matrix? This is the nearest matrix to this in the Frobenius norm. So that is the non-explicit way of doing it. But there's an explicit way of doing it as well, which is using Cauchy's integral formula. So the pi x is actually equal to a contour integral over these ax's, where this ax is this quantity. So you take this quantity, do a certain contour integral, you get that quantity. And this can be used to get dimension-free quantitative form of the implicit function theorem. I mean, this together with the implicit function theorem will give a theorem which is that if you have noise that is small, then the reach is at least then the reach of the output manifold is at least this much, and the Hausdorff dimension is order sigma squared. So to conclude, we bring down the Hausdorff distance between the true and output manifolds to sigma squared d, while bringing down the sample and computational complexities to depend only on the intrinsic dimension. This was dependent on the extrinsic dimension in the previous work of Genovese and Genovese et al. Thank
you. The Charles Fefferman, is he the fields medalist from Princeton?
Yeah.
Okay. The other question I had, so you gave a lower bound on the sample complexity needed. Is that tight?
That was the upper bound.
Oh, that is an upper bound. Sorry. I mean, you give an upper bound. Is that tight? Is that?
So it's close to tight because in the k-means case, which you can think of as the zero-dimensional manifold case, there is a lower bound of k by epsilon squared if you want to get to within epsilon in the empirical risk versus true risk.
I see.
And that k is v over tau raised to d in our setting. So it's close to that. But even for k-means, it has not been settled. So the upper bound is some k log k by epsilon squared or cube or something. And the lower bound is k by epsilon squared. So it's off by some logarithmic factor in k. So we got a power of 4 in this work, but it was later improved by I'm missing the name for somebody. A couple of log factors were shaved off. And
the last question. So when you have these tangent spaces and you're like stitching them together, where do you make sure that they don't sort of intersect with each other?
It doesn't matter if they intersect.
Doesn't matter?
No, because in a sense, what is getting stitched together is two objects. Firstly, the square distance to these disks. So it's a full dimensional object, it's a square distance, and that is getting stitched together with the square distance to this disk by means of that partition of unity. So that is one object, that is f of x. The second object is pi x, which is obtained by stitching together the matrices this is stitched together, obtained by stitching together the matrices ax. Sorry, not ai. So how do you stitch together these to get these projection matrices? You have projection matrices in every ball given by projection onto the ortho complement of the disk. You take this moving average of these things. So you have bump functions on every supported on every ball, which is alpha I of x, and you compute this thing, which is a spatially changing function. And then you compute the nearest projection matrix like this. That is pi x. And then the manifold is given implicitly as pi x of f of x equal to 0. So this is the equation. So it's indirect. So maybe I should mention, so you had initially no, so I think does this also address some question you had asked earlier?
I had asked earlier, do you get some kind of oracular representation for the manifold?
Correct. Yeah, exactly. So because of this, this is actually the solution of some equations which are well conditioned in the following sense. It looks a lot like you have the gradient squared. You have the let's say the square distance to this unknown manifold is what is given to you. So you can do gradient descent. What is actually done is something slightly different. You can do gradient descent along the directions where the Hessian is large. This got a name, subspace constrained, mean shift or something. So you do that, and it will take you to the point, a point pretty close to the best point on the manifold. So yeah, so that.
I had a quick question. So the classical work of Nash tells us that all Riemannian manifolds can be isometrically embedded in D plus 2 or something.
Correct.
Recently, this work was algorithmatized, not to D plus 2, but we now have an algorithm embedding of isometric algorithm of isometrically embedding Riemannian manifolds into basically the intrinsic dimension plus some.
It's not plus. I think it's quadratic, but yeah.
Oh, okay. Are you talking about Nakul's result?
Yeah.
I was talking about Nakul's result.
Yeah,
Can that be an alternate way of solving this problem? First embed it and then verify whether there was enough distortion or not, because if there's no distortion, then...
So the loss function that I have is defined on the ambient space, right? So that you'll have to preserve the properties of the ambient space also.
It's isometric.
No, but the Nash embedding will embed just the manifold. It won't embed this, say, a tube around the manifold, because that is in some high-dimensional space.
Okay, yeah. But in terms of the final result that we care about, whether there was a manifold or not, can that question be answered? I agree that the specifics don't get preserved.
Yeah, so I don't even have a Riemannian metric over here. So I think there are some similarities, but the spirit of the question is a bit different here, because I'm caring about loss, which is square distance to a manifold, and I'm not asking that the metric is of a particular kind. So this would preserve the metric tensor, but the embedding that it provides will be completely different from the original embedding that you have. So it'll be so.
Okay. Thank you.
So these they're not over polynomials, because so this action of going from here to here, it's an analytic map. This is an analytic map. It was given by that Cauchy integral formula. Well, the equation given in coefficients which are very smooth, I can say that, but it's a closed form also in this. But I don't believe I have the closed form here. So yeah, maybe in the next slide. No. Yeah. So. The best I can say is, that this is what the formula is. This has a closed form in terms of Cauchy integral formula, and this equation. This is essentially given by, again, something like this. That was there on the board. It was summation pi alpha I fi. So it's all closed form, but it's not polynomial.
Yeah. Just a couple of questions. One is, would you know that the negative result, there is no such manifold of dimension D?
Yeah.
Just with this, or is that something that I missed?
No, so I skipped. So the context in the result which was with Fefferman-Mitter was different. There you wanted to know whether or not there's a manifold. The result I spoke about later was one where the generative process involved the manifold. Oh, okay. So, but the previous measure had a twice exponential, doubly exponential dependence on little d, and the reason was that you have to basically do some sort of exhaustive search over a large class of tubes. Within each tube, you can do a form of convex optimization, so it is efficient, relatively speaking. But these tubes are all very different. So it's hard to kind of do an optimization over a space of manifolds, which contains, for example, unions of lots of spheres, a torus, a Klein bottle, etc. They're all completely different objects. So it's a combinatorial optimization question. And there's no easy way of moving smoothly from one to the other. So essentially, if you are within the reach of a manifold, all these manifolds become what are known as sections of a vector bundle over a base manifold. And those can be convexified, and you can do convex optimization over that set. But that is like locally perturbing this base manifold. So you have to essentially look at every possible base manifold at a scale of tau, where tau is the reach, and then separately do it. At least that's what we have done. There may be other things that one can do.
Just one more question. Usually in problems of manifold learning, there's some dependence on the sampling density of the points. So I didn't see anything that you provided. You gave just some endpoints in the.
I think so. Here there was somewhere there was.
Is it required in your?
Yeah. I mean, you require so for example, there was averaging processes that were involved. If you don't have enough points, that averaging process will not do what it's supposed to do. So here, for example, I think I have something. Yeah. So this is the sampling. This is the number of samples needed.
Not the number of samples, also the distribution of the samples.
Yeah, so we assume that the measure is log Lipschitz, and so if you just have enough samples, you'll get a fine net.
Okay. And are there any similarities to this manifold learning in machine learning, like LLE, ISOMAP? They all try to do this disk-like thing, but you have a much more mathematically rigorous formulation. Just wanted to know how do those methods even come close to what you're doing, or
My impression is that this locally linear embedding is a bit like this, but what it will provide you is lots of little pieces, and they won't patch them together. Yeah. So.
Thank you so much. Any other questions? If not, let's thank the speaker again.